I'm Norman Wobbeger. In this video, we're going to carry on looking at the logical difficulties with the modern theory of limits that you find in undergraduate analysis and sometimes calculus courses. Okay, so here is the main definition that we're going to be looking at. There are other definitions of limit too. The problems are essentially equivalent to the ones we're going to be discussing here. Okay, so if S1, S2, S3 is a sequence of real numbers, and A is a real number, then the limit as n approaches infinity of Sn equals A means, okay, here's the definition, here's what this means. It means that for all epsilon greater than 0, and this epsilon greater than 0 is meant to be a real number. Okay, so for all real numbers epsilon greater than 0, there exists a capital N, a natural number, such that if little n is bigger than or equal to capital N, and n is also a natural number, so one of the indices that appears here, then the absolute value of Sn minus A is less than epsilon. Okay. So we looked at what this means last time. We showed you some relatively simple kind of example that illustrates the usual techniques that undergraduates learn to manipulate this definition, and they get the impression that they understand this definition, but they really don't. Okay. So the difficulties with the definition really are sort of threefold. First of all, there's the difficulty in the fact that there are real numbers involved. And real numbers involve an infinite amount of information. So it's logically weak just because of the real numbers that are involved. Then there is the difficulties with the specification of the sequence Sn. The point is that this term sequence has not properly been defined. Okay? In mathematics, we are obliged to define the terms that we use. Terms like sequence, function, number are not exempt from that requirement, unfortunately. All right. So that's the problem here, that we are not saying what we mean by a sequence. And the possible difficulties will become clearer in this video. We're going to see exactly how this ambiguity here manifests itself in practice with this definition. And finally, the third difficulty, and probably maybe the main one that's novel to you, is the requirement to obtain an infinite number of n's. If you actually look at the logical structure, the definition is requiring us to find these capital N's, one for each epsilon greater than 0. That's what it's actually asking. For each epsilon greater than 0, there is a capital N. This means that actually the definition is requiring us to obtain an infinite number of n's. And as we'll see, you cannot calculate an infinite number of n's in general. Alright, so most explanations of this definition in modern analysis courses are seriously inadequate. They really don't work. Most of them illustrate the story with some simple-minded examples, like the ones that I showed you in my last lecture, where there's a functional relationship between epsilon and n, and the idea is to try to establish this functional relationship, and then you get all the n's from all the epsilons sort of at once. But this is in fact rather a special situation, which does not properly reflect the main body of this definition. So most math majors think they understand this definition, when in reality they don't. If they did understand it, they wouldn't accept it as proper pure mathematics. They would be suspicious of it. They would be skeptical. They would voice their objections. Young people are idealistic. They are not willing to accept something which doesn't work just because it's convenient. The only way we slip this by them is by not really fully showing the problems to them, keeping them unaware of the difficulties that are over there in the corner. Alright, so in today's video we're going to have a good look. We'll lay it all out, one example that will clearly illustrate the problems with the definition of the limit. Okay, let me define some kind of sequences, and this is an informal definition that sort of follows the usual practice. We're going to call these extended harmonic sequences. And they're based on this particular sequence, which is in fact actually accessible to us within our framework, because it's actually an example of a rational polynumber on sequence. We're going to call it the harmonic sequence. Okay, it's a sequence given by this rational polynumber 1 over n. And the sequence that generates or determines is 1, 1/2, 1/3, 1/4, and so on. A very simple and natural and important sequence, the reciprocal of the natural number sequence. So I think we all agree that whatever our definition of limit might be, we certainly ought to have that this sequence has limit 0. Okay. Now I want to define a more general kind of sequence closely related to this harmonic sequence. We're going to call these extended harmonic sequences. So what is this? Well, it's a modification of the harmonic sequence where we allow repetitions of any or all of the elements. Instead of having just 1/2, we can have more than 1/2. We can have 3 of them, or 17 of them, or 3,497 of them. We're even going to allow an infinite number of halves. So in other words, that the sequence just keeps on going with a half. So here are a couple of examples of extended harmonic sequences. Here's the first one. 1, 1, half, 1/3, 1/3, 1/3, 1/4, 1/5, 1/5, and then it carries on in some fashion. So we're getting the harmonic sequence here, but we're getting some of them repeated more than just once. There's at least one of every one of these, but there might be more than one. For example, there's 2 1s and there's 3 1/3s, and we don't know how many 1/5s there are because we don't know what the next one is. Here's another one. 1, 1/2, 1/3, 1/3, 1/3. Let's suppose that the 1/3s carry on. Just keeps on 1/3s. We're going to call this also an extended harmonic sequence. All right, that's going to be our definition. Here's another way of saying what an extended harmonic sequence is. It's an inductive definition. All right, so we say that a sequence S is an extended harmonic sequence precisely when, first of all, the first element is 1. And the other requirement is that if the nth element is 1 over k, then the n plus first element is either 1 over k as well, or it's 1 over k plus 1. So if you're going one at a time, let's say your current element is 1 over 7, then the next element can be either 1 over 7 or 1 over 8, and those are the only 2 possibilities. Okay, so you can just carry on creating a sequence, choosing whether you're going to have the same fellow that you already have, or whether you're going to move to the next one. Okay, so note that such an extended harmonic sequence is determined by the sequence of natural numbers or infinity which record multiplicities. In other words, if we keep a record of how many 1s we have, how many halves we have, how many thirds we have, how many 1/4s we have, and so on, keep a record of those, then this record is essentially completely equivalent to the actual sequence itself. So here there are 3 1s, there are 2 halves, there are 5 1/3s, there's a 1/4, there's 1/5, there happen to be 3 1/6s, and so on. But I do want you to remember that we are also allowing the possibility that one of these fractions ends up going on forever and filling out the rest of the sequence. So for example, for this one, the multiplicities would be 5, there are 5 1s, and then 1 because there's 1/2, and 2 for the 2 1/3s, and then, assuming that all the rest of them are quarters, we could put this symbol infinity in there, and then that's all there would be, so that this sequence here is recording or describes that extended harmonic sequence. Alright, so what we're doing here is instead of thinking about all possible sequences, I'm kind of restricting my attention to a rather special kind. There's still quite a lot of variability possible, but all the elements in the sequences we're going to consider now are of a very particular kind, starting with 1, then halves, and then 1/3, and then 1/4, and so on. And I want to look at one particular such extended harmonic sequence in particular. And it's associated to one of the most interesting unsolved problems in mathematics, the Collatz conjecture. Alright, so very easy to state situation. If you want to have some more information, have a look at my famous math problems number 2, which is all about the Collatz conjecture. Alright, so to generate a Collatz sequence, we start with a natural number n, like 1 or 7 or 349. If n is odd, we compute 3n plus 1. Multiply by 3 and add 1. If n is even, we compute n over 2. We divide it by 2. And we continue. So we start with some natural number, whatever it is, and then we either multiply by 3n plus 1 or we divide by 2, depending on whether what we have is odd or even. And the Collatz conjecture, sometimes called the 3n plus 1 problem, has some other names as well, is that eventually you get the number 1. No matter what natural number n you start with, eventually you keep repeating these two operations, eventually you get down to the number 1. It's such an easy to state conjecture, it's so enticing. You can play around with all kinds of different numbers and see that it seems to work all the time. But how it does so and why it does so is very mysterious. There's not any clear pattern that allows you to predict in advance how long it's going to take for this Collatz sequence to eventually get down to 1. So let's get a little bit of experience. Suppose we start with the number 1. Well, in that case, we're kind of finished because we already have 1. So we have 1, we can stop. If we did keep on going, we would multiply by 3 and add 1 to get 4. We would divide by 2 and divide by 2 again, we'd be back to 1. And the cycle would then repeat if we kept on going. If we start with 2, it's even, so we divide by 2 and we get 1 immediately at the next step. If we start with 3, then multiply by 3 and add 1, we get 10. Divide by 2 to get 5. Multiply by 3 and add 1 to get 16. And then a couple of divisions of 2 gives us 1. If we start with 4, well, we already know what happens because it's contained in here. If we start with 5, we already know what happens because it's contained in here. So the next new one is 6. We would have to divide by 2, and then we would have 3. And then at that point, we already know what happens because we've already figured out what happens with 3. We would get this sequence here and eventually get to 1. With 7, it's a little bit more interesting. Multiply by 3 and add 1, 22. Divide by 2, get 11. Multiply by 3 and add 1, 34. Divide by 2, get 17. Multiply by 3 and add 1, get 52. Divide by 2, divide by 2. Multiply by 3 and add 1, divide by 2, divide by 2, we get 10. At this stage, we already have a 10 there. And we know what the answer is. It's going to get to 1 in 6 more steps. So you can test it out for yourself. It's been checked out to many billion. It always seems to work. But nobody knows whether it in fact always works, even for a very, very large n. Maybe there's some really huge number n for which it does never get to 1, and this sequence just keeps on going higher and higher numbers, up and down, but keeps on going up and up and up. We don't know. Okay, very famous unsolved problem. Okay, so now here is the main object for this lecture. It's what I call the Collatz extended harmonic sequence. It's an example of an extended harmonic sequence. In fact, it's the only example that we're interested in today's lecture. Okay, how do we generate this? Here it is right here, at least the start of it. Here's how we generate it. We start with the number 1, which we have to. Okay? And we sort of think of having a seed, which is over here. This is sort of an auxiliary sequence that helps us generate the actual Collatz extended harmonic sequence up here. So the seed is 1, and we have a 1. What we do is we are going to run the Collatz sequence on 1 until we get 1. Well, it's already 1, so we're not going to do anything. So what we're going to do is we're going to move to the next seed, which is the next natural number, bigger than the one that we just had. So our seed goes up from 1 till 2. And what we're going to do now is we're going to have a whole bunch of halves, reciprocal of 2. And how many of these are there going to be? Well, as many as we have in the Collatz sequence that generated by 2 until we get 1. So we're going to run the Collatz sequence starting with 2. And I remind you that was just 2, and then we divided it by 2, and that gives us 1. So for each one of those elements of the sequence generated by 2 in the Collatz game, we're going to write down a half. Once we've gotten to the 1, we're going to stop with 2, and we're going to go to the next seed, which is 3. And we're going to go to the next reciprocal, which is 1/3. Then we're going to run the Collatz game again, 3, 10, 5, 16, 8, 4, 2, 1, until we get a 1. And for each one of those, we're going to record a third. Once we have 1, our seed is going to bump up to 4, and we're going to write down a reciprocal 4, or a quarter. And then we're going to run the Collatz game again until we get 1, all the time writing 1/4 consistently, until we get a 1. When we have a 1, we bump up the seed to the next one, drop the reciprocal to the next reciprocal 1/5, and carry on. So I hope it's clear how we're going to generate this Collatz extended harmonic sequence. The number of 1/5 is going to be determined by the number of steps required in the Collatz game to go from 5 to 1. Once we've gotten down to 1, we're going to stop with the 1/5, and we're going to move on to the 1/6, and then the 1/7, and then the 1/8, and so on. This is a very computable sequence. If you are a computer programmer, you will easily be able to write down a program that generates this sequence, probably only in a few lines. It's an excellent exercise. All right, so exercise for programmers, write some code that generates this sequence. Then you can get your computer to run it, and you can tell us what is S of 100. What's the 100th element in this sequence? A little bit more ambitious. What's the 1,000,000th element in this sequence? Okay, so now we know what this Collatz extended harmonic sequence is. Here is the $1,000,000 question. What is the limit as n goes to infinity of Sn? What's the limit of this sequence? Well, the limit is 0 precisely when the Collatz conjecture is true. If the Collatz conjecture is true, then the limit of this sequence is 0. Why? Well, because then every seed that we stick in, the Collatz conjecture will tell us that eventually we get to 1. So there's only going to be a finite number of reciprocals of whatever seed we start with. And then we necessarily eventually move to the next seed, which is a little bit smaller. There may be a long string, but eventually we're going to get to the next one, and then to the next one, and so we're going to eventually make our way towards 0. However, if the Collatz conjecture is not true, and somewhere way out there there's some really special number for which the Collatz conjecture story just keeps on generating higher and higher numbers and we never get down to 1, in that case, this Collatz sequence will have the property that it's going to carry on with 1/n, 1/n, 1/n infinitely often for that particular n that has that property that disproves the Collatz conjecture. So this is a very interesting situation. How are we going to tell what the limit is. And how are we going to prove what the limit is? You see, this is very different from the baby examples that you're shown in calculus and analysis texts. In this example, the full force of the ambiguity of the potential infinite aspects of sequences comes to the fore. The fact that we may have a lot of control about the sequence in some sense, namely we have a computer program that will generate the sequence very reliably for us. But nevertheless, mathematically, we don't have enough understanding of the underlying mathematics to be able to tell what actually the sequence is doing. So I think we can see the problem here, that if we want to get n's for every epsilon, suppose we agree that the limit is 0, and we have some epsilon, let's say 1/4. Okay? So we'd like to know how far do we have to go in this sequence before we can guarantee that all the elements will be less than 1/4. Well, we can see exactly where that position is. It's right here. Okay? There would be the n. The n would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If little n is bigger than or equal to 15, then the nth term is less than 1/4. But how far we had to go depended on how many of these strings were in all of the Collatz sequences up to that n. We had to know how long we had to run the Collatz sequence for 4, and how long we had to run the Collatz sequence for 3, and for 2, and for 1. So there's no way with present technology that we can find some functional relationship between epsilon and n, even if we do have a lot of confidence that the limit is 0. Okay? There's no escaping the fact that if you don't actually know the Collatz conjecture is true, if you don't have the proof of the theorem, then you are forced, if you want to check this fact, to come up with an infinite number of n's for an infinite number of epsilons, requiring an infinite amount of time, an infinite amount of computation, in order to establish this limit. What's underlying some of this discussion is the fact that there's a very important dichotomy in the approach to infinite sequences, whatever they might be. So anybody who believes in infinite sequences really has to belong to one of two camps. There's a choice approach to sequences, and there's an algorithmic approach to sequences. For finite sequences, the difference between these two approaches is relatively minor. It's a difference, but it can be overcome in most situations. With finite sequence, we most of the time require that we actually specify all of the elements of the sequence. We write them all down explicitly, and then we can honestly say there is the sequence. One approach to infinite sequences is that we believe that we can write down each of the elements of the sequence independently of all the others. We can basically make the infinite enumeration. Another approach to an infinite sequence is to say, no, we're going to stick with sequences which are finitely specifiable. That there's some algorithm or procedure or law that generates the sequence. In the one case, we are happy with having an infinite amount of information required. With the other one, we're more computer-oriented and say, no, we need a finite amount of information to specify this infinite sequence. It's important to realize that there's a fork in the road here. Okay? The theory of infinite sequences is dramatically different if you view it this way or you view it this way. And anybody who's serious about logically getting on top of this has to make a choice in their own minds as to whether they're going to take this position or this position with respect to infinite sequences. You might like to ask your local analyst which of these two camps they belong to. Officially, the position is that pure mathematics in the year 2014 more or less is in this camp. That's the official doctrine. But I suspect that if you actually did a straw poll of mathematicians, you'd find that there are quite a lot of people who have heretical positions and are actually much more comfortable with this position, even though they may not come out and say so. So here is a sequence, but you only see numbers written down, separated by commas, on this strip of paper which keeps going in that direction. So there's an infinite strip of paper going in that direction, and if we pulled on this tape, well, we would be able to see more and more entries. But there's no rule written down anywhere. Nobody has told us of an algorithm or a procedure that generates this particular sequence. So there's no guarantee that we have to be able to predict what the next one is. The next one might be 1/5, or it could also be 3,479. Okay. So this kind of sequence where we have no rule, there's no procedure, we just imagining that the whole sequence is on this infinite tape. This is a kind of object that people who believe in the axiom of choice say, yes, that's a legitimate mathematical object. Now, if you actually look at this one, you will say, wait a minute, doesn't that look like the Collatz extended harmonic sequence that we were looking at before? There's 1, 1, there's 2 halves, there's 1, 2, 3, 4, 5, 6, 7, 8, 1/3, there's 3 1/4. It certainly initially looks exactly the same as the extended Collatz sequence. Maybe it is the same, but maybe it's not. So suppose we were asked to work with this sequence. Suppose somebody asked us, what is the limit of this? Find and exhibit the limit of this sequence. Now there's no possibility of going to the Collatz conjecture and proving it. In the previous case, when our sequence was given by an algorithm generated by the Collatz sequence, we at least had an outside chance of some smart fellow coming along and proving the Collatz conjecture, which then establishes that the limit is 0. Here there is no connection directly with the Collatz conjecture. There's no way we can actually prove anything about this sequence. There's only one way to see what the limit is, and that's by scrolling more and more and more and more and more, all the way to infinity. Now, for this kind of sequence, if you want to exhibit an n for each epsilon, my friends, I'm sorry, but there's going to be an infinite amount of work required. Not just an infinite amount of work times 1, it's actually an infinite times an infinite amount of work. For example, let's say for the epsilon equals 1, you want to find out how far you have to go before you can be guaranteed that all the numbers are less than 1. You will have to go through the entire tape, all the way to the end, to infinity, and establish where the last thing that's bigger than or equal to 1 is. Okay, maybe it's here. Maybe it's somewhere far down the track. In any case, there's no way you can tell what the n that goes with 1 is until you've looked at the whole sequence. So there you have the n for epsilon equals 1. Great. And now you get to find the n for epsilon equals 1/2. Again, it's not enough just to go there and say, well, it looks like it from now on. No, you have to wind up the tape and you have to look at the entire infinite tape yet again to determine where exactly it starts becoming less than 1/2. Then you have to do the same thing for 1/3 and the same thing for 1/4. So there's an infinite amount of infinite searches to be done to establish that this limit is whatever it is. And this is the story necessarily with any sequence which is determined by choice. So if you believe that infinite sequences are in fact all determined by choice, then necessarily you're putting the onus on you to do an infinite times an infinite amount of work every time you want to verify a sequence's limit. Because there's no algorithm or function or rule to generate it, it's just given by choice, it's an infinite tape, you have to look at the whole thing to be able to decide what the limit is. So those of you who are not professional mathematicians will say, wait a minute, why in the world would professional mathematicians choose choice over the much more sensible algorithm approach? Clearly it's much more sensible to think about infinite sequences as being generated by algorithms. Wouldn't you think? Just to wrap up, let's have a quick look at some of the pros and cons of choice versus algorithms. So, the choice approach to sequences, it does have some advantages for the modern mathematician. Namely, you don't need to fuss around with programming languages and algorithms. You don't have to have a prior theory or understanding of algorithms, which is in fact itself a whole knotty subject. Not at all so obvious how to set that theory up mathematically, and something that most pure mathematicians aren't entirely comfortable with. So by thinking about choice as our way of thinking about infinite sequences, we can avoid those issues. The cons to a choice approach to sequence include the fact that you can't explicitly exhibit any examples. You can only exhibit examples of the kind that I showed you, where you go up to a certain point and then you put 3 dots. You cannot actually exhibit in its entirety a full choice sequence. They remain somewhere in the never never land of dreaming. And furthermore, you need to rely on an axiom of choice. It really is an axiom, a religious position that says, yes, we can do this infinite process, even if, in fact, we can't. We'll just pretend that we can. We'll just make it an axiom. Let's have a look at the algorithmic approach to sequences, which I have a lot more sympathy with, okay, a lot more sympathy. But we should appreciate that there are also pros and cons to it as well. The pros are that, first of all, it fits with a computational approach. This is what modern computers kind of do, so it makes a lot of sense to talk about algorithms and so on. There's lots of examples. Any sequence that you or I generally use or know about is a computationally well-defined sequence. There's an algorithm that can generate it. So most of the standard sequences that you find in analysis and so on, they're all of this kind. That's an advantage. The cons with this are, it's very tricky to define equality of algorithms. And it's not entirely easy to define even what an algorithm is in the first place. You also need to worry about algorithms not finishing. Sometimes you may have an algorithm that goes into some kind of loop. How do you detect that? That's going to mess up your computer program. In other words, if you're going to rely on computer programs for sequences, you have to worry about bugs. And then there are Church-Turing kind of issues that we'll talk about later on in this course, but it's not entirely clear that what a computable sequence is independent of what machine you use or what programming language you use. It's a very delicate, subtle issue. Okay. So there's difficulty with both of them, and at the very least, you should demand of your calculus instructors and analysis instructors that when they're talking about sequences, if they are going to talk about infinite sequences, they may not be willing to address the issue of what a sequence actually is, but at least try to get them to clarify whether they're talking about sequences which are algorithmically generated or generated by just making an infinite number of choices. The issue was already understood very well by the brilliant philosopher, the 20th century philosopher Ludwig Wittgenstein, who stated, he was a strong critic of a lot of modern mathematics, and at one point he stated the following: "The mistake in the set theoretical approach consists time and again in treating laws and enumerations as essentially the same kind of thing, and arranging them in parallel series so that one fills in gaps left by the other." So when Wittgenstein talks about laws versus enumerations, he's talking about algorithms versus choice. It's exactly this dichotomy. And he recognized, even back then, in the mid of the 20th century, that the analysts were basically trying to play a game, having their cake and eating it too. It doesn't work, and I hope you've seen that the modern theory of limit is essentially, intricately linked with having to do an infinite amount of things. Something that you or I cannot do. And there's no need that we should pretend that we can do an infinite number of things. If we could do an infinite number of things, we could solve so many mathematical problems immediately, famous mathematical problems. The Collatz conjecture we could just instantly compute. Take us 1 minute to find out whether it's true or not. Point is, we cannot do an infinite number of things, my friends. Never could, never will be able to. That's the reality of the world in which we live in. And there's no shame in being honest about it and saying, yes, we cannot do this, so let's not pretend that we can. In our next video, we're going to look at real numbers as Cauchy sequences of rationals, or more correctly, as equivalent classes of Cauchy sequences of rationals. And not surprisingly, you will see the same kinds of problems emerging there. The theory doesn't work. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.